Okay, so you see my presentation, I hope. And so I'm going to talk very quickly about mostly our experience on remote sensing data for vegetation mapping in one project, which is the ITAREO project, but also a little bit beyond. And this is presentation is by me, but most of the work that I'm going to present is coming from my group under the leadership of Professor Fabio Dell'Acqua. Of course, remote sensing for agriculture and generically vegetation, and I'm seeing also forest as a part of agriculture, although I know that's not completely the same, is very important, is becoming very important, mostly because there are a number of satellites, a number of sensors which are providing data, which is increasingly useful for many different applications that could be helpful for traceability, for getting better agricultural productivities and the management of the resources. Therefore, I'm going to give you two examples of activities. The first one is directly a collaboration project between Italy and Argentina. So it involves Universidad Nacional de Córdoba and the University of Pavia here in Italy, and the University of Rome, and also the University of Molise in southern Italy, with two different types. And this is a project ITAREO, which is the name comes from Italia, Argentina, Earth Observation EO. So it's a mixture of Italy, Argentina, and Earth Observation. And it's for system for the Earth observation in Italy, Italian and Argentinian one, for the mapping of the United Nations Sustainable Development Goal. And the second project is called Multi-Big SAR Data, which is about the use of SAR radar data, multiple sensors. Again, you see that there is a pattern because we are talking mostly about radar in this presentation for environmental mapping, and specifically here we are going to talk about mapping for monitoring activities of organic agriculture. So the first one is the project ITAREO. The project ITAREO is a project which has been funded by the Italian Ministry for External Affairs under the collaboration between Italy and Argentina. And the idea was to use the data coming from two different constellation of satellites. One is the Italian Cosmos Caime satellite, and the other one is the Argentinian satellites, which are going to SAOCOM satellite in order to prove that it's possible to map from space some indicators for the Sustainable Development Goals of the United Nations. Of course, it was about many Sustainable Development Goals in many different areas that are not only related to things that correspond to vegetation mapping, forestry, or water mapping, but here I'm just focusing on those which are more important for your specific interest. First of all, here you see two images that correspond to the two satellite constellation that are used. On the top, you see SAOCOM, which is the Argentinian radar satellite constellation, and on the bottom you see one example of element of the Cosmos Caime, which is the Italian constellation. The project, as I mentioned, was managed by the University of Pavia on the one side and l'Istituto Gulick, the Universidad Nacional de Córdoba, on the other side. We work on many different indexes, Hambre Cero, Agua y Saneamiento, Industria, Innovación, Infraestructura, Ciudades and Vida en la Tierra, but here I'm just talking about some of indicators related to this specific sustainable development goals which are related to vegetation mapping. So, for instance, in terms of so the goal number 2, Ampresero, we worked on mapping different type of vegetation using radar data, integrating the data coming from Cosmos SkyMed constellation and the SAOCOM constellation. And also by considering free data which are available from the Sentinel, which is the European constellation. And we use data fusion technique and machine learning, of course. So we wanted to make a comparison, for instance, with this map. This map is a map obtained by the Instituto Nacional de Tecnología Agropecuarias in 2020. That was using optical data, Landsat 8, and we wanted to, and using a relatively standard random forest machine learning technique. And sorry, I'm wrong. Using a statistical classifier. Instead, we used a little bit more complex random forest classifier. And the idea is that we don't use a single image, but we use a multi-temporal series of data. And this is something that we found out is increasingly interesting and important for obtaining good result. And here you see an example of the two maps. On the left side, alla izquierda, you find the map by INTA. And the other one, which is the map by ITAREO, which is on the right, using, in this case, radar and optical data together. And you see, of course, I can also put the number, but I'm not adding those numbers here. The second map is more precise than the first map, but if you look only at the, let's say, visually to the maps, you see that there is a level of detail which is much better on the right than on the left. Another example is the possibility to map water, and in this case we show that it is possible to use satellite in order to obtain good result in terms of water extent, so how much water we are going to obtain in a specific moment in a specific area, and in a very large area, as you can see from the images. And on the same time also the activity which was made by the performed by Universidad Nacional de Córdoba is about the quality. So you see Lago Losses, the Roque, which is the basin, water basin, which is used by the city of Córdoba, and we were able to analyze both how much water is there and also which is the quality in there in a continuous way. And in order to do that, we also used, in addition to the radar data that I'm showing you, whose result I'm showing to you in a moment, also the result, some analysis made by using the hyperspectral sensor, still from the Italian Space Agency, which is called PRISMA. So in case of water, this is just giving you very quickly an idea why using radar is very good in detecting water, because water in radar data is basically related to black areas. And it's black areas because radar is providing a signal which is reflected by the surface of the water, so nothing comes back to the sensor, and therefore the amount of energy which is received by the sensor is zero, which in our image translates into black. And you see, for instance, on a very big area like Laguna Picasa, you see very clearly that it's black, but also in very relatively small river like Rio Primero, after Cordova, let's say, you see that it is very easy to spot and to find out which is that area. And using this, it's also possible to find out how much water you have in those specific area. The methodology that we developed, although I don't want to be in the technical detail, is a methodology which is based on using a series of data. So not using one single image, but using many different images. This is useful for water, but just to tell you, it is also useful for vegetation, because the idea is clearly that using multiple images, it is possible to obtain a specific pattern of the temporal characteristic of one crop, which is clearly different from the characteristic of another crop. Here we are doing it in order to obtain the possibility to recognize permanent water, so water which is always there, with and temporary water, so water which is only in specific interval of time. And you see that using the same methodologies, it is able on different temporal scales, here, for instance, every year, to find out which is the maximum and also the minimum. Here we are showing only the maximum extent of a specific area, like in this case, Laguna Picasa, where it is clear that in the last 4 years, from 2020 to 2023, the size, the maximum size of Laguna Picasa has decreased by a quantity that was computed as more than 30%. So it's not, it is possible to obtain information about how much water is available, how much water can be used for many different applications, and then make some analysis of what is the trend along different years. The advantage of having multiple sensors is related to the fact that multiple sensors provide multiple ways to look at the same area. So here you see, for instance, on the left that there are 3 images. The first one on the left is the radar image of a specific area. You see in the middle a optical image of the same area. And if you use only the radar image, the result is the blue area, which is the third one, which is clearly wrong, because even if it looks black, this area is actually covered by mud. It's not water, but it's something which is different. And therefore, only by combining the 2 data sets, so the color one, let's say, and the black and white one, which is the radar one, and the optical one, you get the final result, which is the one on the bottom right, which is actually the one that gives you the best characterization of the water. And using this, of course, we made a number of analyses, not only in Argentina, because these examples are in Argentina, but also because the project was Italy and Argentina. We use it also for mapping the water in the Po River, which is flowing in the north of Italy, in order to characterize the problems related to the big drought, so lack of water, that we had in the year 2023. The second group of examples that I'm going to give you are basically related to this other project, which is multi-big-SAR data. Multi-big-SAR data is a project for the temporal sequences of different radar missions, Cosmos Skymed, again, SAOCOM, and Sentinel-1, for 2, and again, it was a project for many different applications. One of them is monitoring of the characterization of organic plantation, in order to identify which is the type of plough which is used, so the tipo de arado, and how much the water is used for rice plantation, because in our area here in Pavia we have a lot of rice plantation. We are one of the big, this area in Italy is one of the biggest producer of rice for the whole Europe. Different plough is basically important because using different type of, in agriculture there is a use of different type of arado because of different type of agriculture. So in conventional agriculture there is a very big or a deep plough. In organic agriculture, instead there is the minimum plot, so a very, very small amount of terrain which is moved. This translates into a different representation of the data. So from radar satellite, it is possible to obtain measuring from the measure of the radar satellite, it is possible to obtain which is the rugosity of the surface, and therefore by the rugosity of the surface to understand whether there is an area which has been plotted in one way or another way. This model is a mathematical model, but as you see, the amount of quantity that comes from the radar, which here is represented by sigma NAF, sigma 0, VV, so polarization, VV polarization, it is possible to obtain ZS, which is the average type of rugosity. And so the methodology is basically, okay, we have a long sequence of data. So we know that when we have a very large backscatter, this is the area of ploughing. And when we are a very low value of backscatter, it is because there is water and therefore it's flooded. So we have a temporal sequence, and by looking at the maximum, we can find out if the methodology, if they use the right methodology, and therefore it is organic plantation or not. And by using the flooding, we know whether they are using a different type of rice or a different type of flooding methodology, which is also an interesting element with respect to this type of monitoring. And here, for instance, you have an example. We use the database of the coming from the Lombardy region that is providing which are the rice field. And then we found out that it is very, not very, but it's actually easy to recognize which area has a processamento minimo and which area has a rado convencional, and therefore it is possible to make let's say a discrimination between organic, or at least the people who are using the same methodology of organic agriculture and people who are not. And clearly you see that many people more are using arado convencional than processamento minimo, but this is of course also a trend which is changing. For the immersion period, and I'm just coming to the end of my presentation, again, we know that it is possible to use a methodology which is called false flooding in order to reduce the amount of weed, so let's say the type of vegetation that we don't want into the field, instead of using chemical products. But of course, this is something that can be seen from the satellite. I have already shown that it's possible to see the water, so we can use this information. But the problem is how we know how long is the time that we consider the water, because clearly the satellite is not providing data every day. And therefore, it is providing data every 5 to 10 days, depending on the different type of satellite that we are considering. And therefore, the biggest problem here was how long has been flooded, how long has the field been flooded. So we use a methodology which is, let's say, considering the temporal series of the data, and then using a temporal filter, the Sabisky-Golay filter. Then we extract a minimum value. On the other side, we also extract the optimal threshold by using a standard methodology for a binary automatic characterization, which is called Otsu thresholding, in order to obtain which are the limit, the starting point and the ending point of the inundation. And here you see, for instance, an example where the sequence of the values correspond to the points. The horizontal line, which is dashed and red, corresponds to the threshold. And then the T flood is the time which we consider as the time corresponding to the flooding of the specific area in a test site that we have close to Pavia in Parasacco. So here are my conclusions. In this example, I've shown you the use of radar, SAR, but I wanted to stress it again, not one single radar, but multi-temporal sequence of radar data, which is available right now because both Italy and Argentina have sensors which are acquiring continuously, and therefore it is possible also by combining the two the two constellations to obtain a very rich sequence of data that can be used. Now, if you have a very rich sequence of data, that means that you need some machine learning approach. And this machine learning approach is the point that we are working on. Because clearly, if you have a more complex data set and you have a long sequence of data, you cannot base your analysis only on very standard characterization, but you need a more complex analysis. And we have shown that by using this more complex type of analysis, it is possible to obtain results which are interesting because they provide input to models, agricultural model, environmental model, also economic model that can be used in order to make as was mentioned earlier, make the mapping of agriculture and forestal element of the surface something which is becoming more and more interesting from the management and efficient from the management point of view. And that's it. Thank you very much for your time.